As it.
Hey, Chandler, get me some.
Okay.
Oh, shit.
That was profound. All right. A couple of little announcements. One of you raised some concerns about the clarity of the stuff that was being sent out. And I talked to Mason, our computer guy, and explored the possibility of doing it with a document camera. He personally thinks that's a mixed bag because I have one of the better computers and one of the better screens, but we may explore that further. What I can certainly do is print bigger, and that's what I'm going to do. So I will print bigger henceforth, and hopefully that'll make it work. Okay, how do I get this to expand? How do I get that to expand?
Double click.
Double click on that, okay. Okay, all right. I appreciate people raising concerns about like the clarity, and sometimes I cover up stuff inadvertently. I don't mean to, of course. And so whenever I do that, let me know here. Now, I would point out that going and telling Keith can't tap out that is not going to fix it, at least not in real time. You're much better off just to tell me, but that's up to you. But I have had very little interaction with people during office hours, so I'm going to change the way I do them. I'll be at home for office hours, and you can send me emails to my home address and include a phone number. And then I'll look at your email, and my typing skills are fairly non-existent. So if it's a lengthy response, I'll be better off talking to you on the phone, and I'll give you a response on the phone. I may send you some sort of email, but I'll give you a response on the phone. So we will have office hours from 3:30 to 5:30 tomorrow, and on Thursday, the day before test one. Okay. Any questions on any of that?
Someone in the chat asked what chapters are covered in test one.
Okay, I'll do that at the end. At the end of today's class, I'll go through exactly what's going to be on test one. Okay, that's a fair question. Okay. In fact, somebody sent me an email wanting to have problem set 2 due today, and I'm sympathetic to trying to not have too much stuff. There'll be no new stuff taught on Wednesday. Okay, and today we're going to do largely sort of review of finite element error analysis, which we've already covered. So I think, what's on today's lecture is certainly examinable, or I'll tell you when it's not. And I'll go through at the end of the lecture what's going to be on test, what you're responsible for. Any other questions? Well, let me start off by talking a little bit about stress singularities, because these things occur quite often in practice. We've seen them at cracks, but and a crack certainly has a sharp corner, but other sharp corners do, and generally speaking, at discontinuities. So discontinuity at a sharp corner, the tangent is abruptly changing direction. So that's the discontinuity, but other discontinuities can produce singularities. And these infinite stresses reflect the fact that there really is a high stress there. On the other hand, the infinite stress is not correct. An infinite stress would imply, an infinite stress concentration factor would imply that if you just breathed on it, it would break, and that's not the case. Let me show you though. That the stress concentration is big. Here's, I pulled this thing 3 times, and this got a stress concentration, and it didn't break after 3 times. Now, it might be if I kept doing it, did it 60 times, you start to get a little fatigue crack initiate here, and then it would break. On the other hand, if I do this for this thing here, it breaks. So it's a higher stress concentration than this. So there is a real stress concentration here. Okay? If we went and did a more sophisticated analysis, and you put in cohesive flaws and stuff like that would be quite hard to do. You could get rid of this infinite stress, but you'd get a large stress by and large for these things. Okay. But here's the key thing. You don't want to do finite element analysis of these things. It's an absolute waste of time. I mean, it's not going to converge. So it's never going to get convergent stress there.
What's that F word?
Converge.
F word, FEA of singularity.
Of a singularity, it's futile. Okay, a waste of time. And the stress, whatever stress you get, and whatever value you get, there's an infinite error in it, and it's meaningless. Okay, so you want to avoid this. Okay, and we'll talk about how to do that. The second thing I want to recap is something that's important. It's a verification. This is checking the stresses. Okay. Is the code you're using correct? Well, if you use one of these standard codes, ANSYS, Abacus, Nastran, or the code underlying SolidWorks, those have been pretty carefully checked. If you're using a different code, you really ought to spend some time doing some test problems to make sure it's actually working. Then another part of verification is, are you giving the right input to the code? And this may not simply be a mistake you've made. Some of the documentation of these codes leaves a bit to be desired. Okay, and so it's a little ambiguous, but that's something you need to get right. And there's a book here, and I'll give this reference later. We're going to do an example for this book, but there's this book, and I'll write this reference down later. The one good thing about this book is they have sections where they set out line by line instructions for using answers. And so if you start to use answers, this is a good book to get because it'll help guide you, and you can do some of the problems that are in this book and make sure you're beating this problem. Once you beat these two problems, then we have discretization error. Everything I'm telling you about works also in 3D, but without our conversation is focused on 2D. And if you have a 4-node quad, which I've been calling 4Q, that's in 2D. It's not necessarily a rectangle, okay? It doesn't have to be rectangular. So then there's a node on each of the corners. And what this element does, it approximates the stresses with constants. Basically, it's what it does. So if you have a stress in here in the x direction, it's got a constant value. In the y direction, it's got a constant value. And that constant value might be the value of the actual stress at the middle point, maybe, but that stress is varying. But if you make these elements smaller, the amount of error that variation produces gets lower. On the other hand, if you use 8-node quads, then you have these same 4 nodes on the corners, but at the midpoints of the sides, you also have other nodes. Okay? Each of these nodes produces degrees of freedom. The stresses in these goes lines, okay? So sigma x in here would vary in the x direction and the y direction, okay? Now it varies linearly, and the actual stress may not vary linearly, may vary somewhere other else. So there's going to be some errors here, but the errors are going to tend to be less. But you shouldn't necessarily think that these elements are much better than this, because all these extra nodes are degrees of freedom you have to solve for in the finite element code. And so you've got more degrees of freedom here. And you could compare this with perhaps, how about if I put in 4 of these 4-node quads, then I'd have the same number of elements. Well, then the size of my elements has gone down by a factor of 2 compared to here. So it's not, you don't want to think that these are necessarily better. Sometimes better, but not always. And these are the 2 most commonly used elements in practice. This is what verification is, making sure you're running the code correctly, runs correct, the code itself is correct, you're running it correctly, and then you've got enough elements that you're getting good answers. We'll go through that. Validation, different word, is comparison with experiments. Ultimately, in engineering, we need both. On the other hand, there's little point in comparing with experiments until you've verified your stress analysis. I have seen an instance where the finite element analysis compared well with experimental values, and both are wrong. So you need to verify your finite element analysis first, and then compare with carefully verified experiments. So we're going to start talking about this part, the rest of this recap. And to check for convergence, you have to refine your mesh. You have to refine your mesh reasonably aggressively. If you don't change your mesh much, then things won't change much. And you can end up concluding you converge, but in fact you haven't. And a fairly aggressive way of doing this is to halve element extents, at least on average. Now these element extents won't be constant throughout your mesh, they'll vary. So this is what you do for each one, even though it's different as you go through the mesh, you keep halving it. What's going to happen as a result, in 2D, your number of elements are going to go up by a factor of 4. Okay. I think the last time I left off this -1, somebody corrected me. I much appreciate if you see anything wrong, let me know. Okay, thank you. And in 3D, it'll even be 8. Okay. What this means is, if we're going to do a convergence check, you want to start with the coarsest possible reasonable mesh. Okay, with some experience, you get an idea of that. You don't want to start with a really fine mesh, but even if you did, you could coarsen the meshes to check for convergence. You could go backwards. Okay. Then I gave you a convergence check. Once you refine your mesh like this, you look at how the stresses are changing. So in a given finite element analysis, there'll be some stress that you're concerned with. It may be that things have been breaking, so there's an area that you're going to need to look at. Or maybe you're doing a new design and you want to make sure things don't break. And so you're going to start checking for the maximum stresses. There may well be more than one location that you're interested in a design. Okay? That can happen. And so, but once when you do a convergence check, you do them for one stress at one location at a time. Okay? So you pick the stress of interest. It may well be the maximum tensile stress. It could be the maximum shear stress at a given location. Then you just monitor its values. So this thing here could be a shear stress. Okay? This is the value from the preceding mesh. This is the value from the next mesh that's been refined in accordance to this. And you're looking at the changes. And we're going to require the changes do two things. In an ideal world, you say to be 0, well, that's fine, you can quit. But but that's not going to happen. But here are our requirements. We want the stress increments to be the same sign as you refine. That just is the same sign. This increment going from m-1 to m, this increment going from m-2 to m-1. Okay. And then we want them decreasing in magnitude. And we don't do anything until we've got this. I'm going to refer to this. Let's just call this 1. These are our convergent requirements. Okay. You don't do anything until you've got this. You don't estimate errors. You don't report a stress. You don't tell anybody you've got the stress there. You haven't got anything yet until you're starting to get this. When you've got this, though, you can now go ahead and estimate the errors. And I derived this estimate but you can relax about the derivation. I mean, that was just to show you where it came from. It's not examinable. Okay. Hopefully it wasn't too bad. Okay. So you only estimate errors when we've met the requirements. You only report an error, a spinal stress, if you've got an error estimate. And our estimate of the absolute percentage error for mesh M, epsilon M, we put a hat on it to say it's an estimate. If it doesn't have a hat, it's an exact value. In a test problem, you would know it. It would just simply be your sigma M, the difference between that and the exact answer divided by the exact answer multiplied by 100. But when you don't have the exact answer, then we're going to estimate it with the change. Since it's percentage, we're going to multiply it by 100. Divide by the best value we have, the absolute value. And then there's this expression here, which reflects the rate of convergence of what it's doing. And with this here, this will be bigger than this, so this is going to be bigger than 1, so this number is always going to be positive. I didn't do this, but you don't have to report these, but they're somewhat interesting. They have certain values. We had, during the derivation of this, we had something like 2 to the cm hat equals delta sigma m minus 1 over delta sigma m. If you take logs of both sides, you get log of 2 to the cm, that's cm log 2. And log of this equation, you divide through by log 2, you'll get that cm hat. Again, it's got a hat on it because it's not the actual convergence rate, and it's an estimate of the convergence rate. Under 1, these two will be the same sign. If they had different signs, the log of a negative number, that's an imaginary number, okay, it's a complex number. And moreover, because this is bigger than this number will be bigger than 1, so this will be greater than 0. If this didn't hold, this would be less than 1, this would be negative convergence. Okay? So it's consistent with 1. CM hat tends towards 1 for 4Q. Why is that? Well, 4 Q elements have constants, so the thing they're missing is linear, and that's to the power 1. On the other hand, CM hat ten to a 2 for AQ. For AQ elements, okay? That's because AQ elements have linear functions, so the first thing they're missing is quadratic functions and the 2. Now, that's not strictly correct because some of these stresses don't have Taylor series expansions, and they're not just powers. But this is generally what you expect to happen. On the other hand, these things are more expensive in terms of degrees of freedom. Well, are there any questions on this? Okay, that's a recap of everything we've done. Now, I'll do some examples. Let me give you, here are some references for this stuff. And I put this in on Moodle. I posted this morning. Third post, point 3. So don't bother writing this down. But there are 2 very good books, one by Patrick Roche, Bill Overkamp, and Chris Roy. And these concern verification and validation. And at some point, when you get out, you may want to get these. I know Patrick Roche quite well. He's a character. And I have a slight preference for this book, but this is a very good book. When it comes to solid mechanics, ASME has got a couple of standards. Okay? And so if you end up doing a lot of that, you want to get these. And then there's some relatively recent papers which go through these convergence checks and how to avoid computing a stress at a singularity. Okay? And so when you get out, you may want to look up some of this stuff. I tell you, right now, none of this stuff's examinable. You don't need to go get this, worry about it at all. This is just for your reference in the future. Okay? And as I said, you don't need to bother copying it down. But that was in response to somebody's question about where would you find it. It's certainly not in your book. But if you look at this stuff, it's relatively recent. 9, 10, 6, 12, and then these 16, 18, 19. So this has become, people become more aware that you need to do this because there have been a number of screw-ups in engineering as a result of not doing these checks properly. And if we have time, I'll go through one from industry at the end of today's class. Let me do an example. This is from the C-clamp report, okay? And it turns out that it's possible to construct a test problem. So this, we'll check and see how well these things work. In example 9, I got some error estimates for the C-clamp analysis, final analysis done by AJ. And you don't really know how good those are. So one of the things we did was set up a test problem, which we knew the answer, which was like the C-clamp. It has the same geometry. It has a similar KT. We made it a little bit higher to make the problem a little more difficult. And it has an exact answer. And that's done by superimposing 2D elasticity fields. Okay. It's beyond the scope of our class to discuss that exactly, but it can be done. And what these are called then These are called tuned test problems. They're test problems because you know the exact answer. They're tuned because it has the same geometry and a slightly higher KT to make it slightly more difficult. You analyze it with the same, sorry. As we used on the original application, which was last lecture. And here's what we've got. These meshes have their number of elements going up by a factor of 4, very, very close. Here's what sigma m was. Okay. Stresses, we're really only interested in 3 figures, but we're going to take the differences of these stresses, get these stress increments, and we'd like to have 3 figures for the differences. So that means we end up with 5 figures here. In fact, we don't quite get 3 figures, but we get close. Okay. So the difference between this and this. Difference between this and this. You can see it's gone down about 0.02. This is about 0.01. So 1 is satisfied. The stress increments of the same sign and decreasing in magnitude. They're almost halving, okay, which is what you expect with linear convergence. The exact answer for this problem? And all zeros for the rest. That's completely exact answer. So this, in fact, 1 says they're converging, and these numbers are moving towards them. They haven't got there, but that's getting pretty close. In fact, if we're going through 3 figures, this would be 2.67. The actual answer to 3 figures is 2.68, which is pretty good. In fact, in practice, that would work reasonably well. 3 figures is nice, but not necessary.
So where'd you get the 2.68?
That's the exact answer. Sorry.
And that was given.
That when you construct this test problem, you have an exact answer. Okay, so you set this thing up to give an exact answer, and the exact answer we picked was about 10% higher KT than the original problem. Let's see the original problem. Oh well, oh yes, it was 2.44. Okay, and so we added a bit to that, made it 2.68. But yes, don't worry about how you do this. This is not something you can do right now. Not with what you not that there's any reason you couldn't do it if we trained you to do it. But we haven't covered how to do that. Okay.
Below the sigma or below your change in stress values, is that a CM?
That's an E, sigma exact.
No, not there, right? So you have your columns.
Yes.
You have your delta stress on the very
Yes.
right, and below your delta stress column, there's a CN.
That's 1.
Is that?
Equation 1 is satisfied.
Oh, okay.
Okay, one is this. Okay, so you always check for convergence. Same sign, the same sign, and reducing your magnitude consistently. So one is satisfied throughout this. Okay.
And you only really needed like to check that 3 times for you to determine
Every
that,
time,
yes.
every time when you get 3 mesh results, you'll have 2 increments. You can go and check once. Every time you have 2 stress increments, you can go check once. Okay. Okay. And so this is one check here, the same sign and decreasing. Here's a second check. So this one holds here and one also holds here. So we can get error estimates for this and for this. We can't get an error estimate for this. We haven't passed the conversion check yet. We've only got 1 increment. We can get an error estimate for this and an error estimate for this. Is that okay?
Yep.
So now we can get these error estimates. That's terrible. Okay. For mesh M would be, let me reiterate the formula. You've already got this, so you don't really need to write it down. I'm just putting it down for completeness. So we could get epsilon 3. Delta sigma 3, this is 0.081, 018, sorry. The value of sigma 3 is 2.6637. Then we have this quotient, 0.0360, 0.0181. Actually, I could multiply both of these by 10 to the 4th, and I just put 360 over 181. The quotient will not be changed by multiplying them by 10 to the 4th minus 1. If you compute that, get 0.69%. We could also calculate an estimate of the convergence rate. I had that was log of 360, if you like, 0.0360 over log of this, log of delta sigma m minus 1 over delta sigma m. This is very close to 2, this is 2, and so this quotient turns out to be 0.99. So it's behaving like you'd expect for 4-node quads. Okay. Oftentimes it's not as close as this. It will eventually get close to 1. We could go get what epsilon 3 is. That's 0.68%. So for this particular problem, there's good agreement between the estimated error and the actual error. We can do this for mesh 4 too. Here's a summary of what happens. I just do the same sort of thing but for 4. Then I'll get the following little table. .69. And if I redo it, well, because it's converging linearly, you expect about half. In fact, that's what you get. Not quite, a little bit more than half. From a practical point of view, these are both close to 1. It's about what you expect. When you're doing finite element analysis, you're looking at somebody else's finite element results, the CM hat may not get to 1 for quite a while. And you could say it moved away. Well, that's negligible, really. What this thing reflects, this is linear convergence, so here is a halving approximately. This is not quite halving because this is not quite 1, but it's going down by close to a factor of 2. This is likewise. And what's good here is epsilon hat is close to epsilon m, but slightly bigger. There are some reasons why it's slightly conservative, okay? But it's a pretty accurate estimate. Any questions on that example? Well, let me give you the big picture. Yeah. When you're doing this in practice, the first question you have to answer, what stress do you want to know? Okay. Usually, sigma max at a location which is either failed or has potential failure. By failure location, I don't necessarily mean the thing has failed. You may be designing it and you're trying to prevent it from failing there. So it's a potential failure. Or it may be, and this is very common in design in practice, that you're doing redesign because things have failed, and in fact it is, strictly speaking, a failure location. The next question you have to answer is how well do you want to determine it? And that will depend in practice with what you're going to use it for, what you're going to compare it with, what other strengths you're going to look at, and so on. Okay. Pratt & Whitney, I was working with them recently for a little bit, and for some reason they put 2.6% as kind of a good value for them. I don't know where that came from, must be past experience. Let me give you the error levels for this course. So the answer to this question will be use these error levels. When you get out in practice, you may pick slightly different ones. So there's nothing sacred about these, but these are what we're going to use. You won't have the exact error, so it's going to be an estimate. It'll be initially a test problem. If it's less than 5%, that's satisfactory. Some people might say 10%. Okay, that's what we're going to use in this class. In today's computer facilities, that's quite reasonable. We go down by a factor of 5. Then less than 1% certainly be satisfactory, but we'd call it good. Okay. And this is probably all you really need in practice for the most part. Okay. And so the Pratt & Whitney number of 2.6%, somewhere between here, kind of consistent. And it may be when you work for the oil and gas industry that they'll say 5% is good enough. They have big enough safety factors. They're not transporting. It's not like when you build jet engines, you want to reduce weight to increase performance. Reducing weight costs save you a little bit of money in the oil and gas industry, but it's not that big a deal. So this will vary. consistent with this, we go down by another factor of 5. Less than 0.2% or 1/5%, we can call it excellent. And there's really little point in going much better than that, because when we start talking about the strength, you're going to find the variation is such that it's at least 10%. And so when you're 1/5%, you're 50 times less error than what you're comparing with. And that's good enough. I would say people that go much less than this are probably academics writing a bunch of papers. In practice, you don't need it. So if we go back to what we just had here, then this here is less than 1%, so this is good. And in fact, it is good. And this here stays at
I
good.
don't know about that. I took the intro, but
Sorry?
I don't know if I'm gonna follow through all the classes.
You need to put your things on mute if you're going to have a conversation. Okay, so this is what we're going to use in this course.
Oh shit.
Let me start a further example. So I'm going to do this problem here. This particular problem is chosen so we can compare with photoelastic determination. Photoelasticity is essentially experimental approach, and that being the case, then we'll be able to validate. Now, when we check for convergence, and that'll be verification. When you compare with experiment, that'll be validation. So this problem, you've got an answer for this problem in your book too, so we can compare with that. So here's the specific geometry. Here's that's the biggest radius you can put in here without getting a sharp corner here. This is actually a sharp. Circular sharp, and it's subject to a moment. For geometry, for this radius r, this is the smaller diameter, lowercase d. Larger diameter, uppercase d. R is small. It's 44th of d. Okay. Then 21/20. I guess R is not quite as big as it could be in this situation. There's a little wee bit of a straight piece to here. Okay. Otherwise, it would be, this would be 1/20th, it'd be 1/40th. It's a bit smaller than that. So if I blow this up, it looks like that. There's a very small piece here. This is what the people who did the photoelasticity did. Here's what the finite element got. We use a different element here. We use AQ. This is really a 3D problem, but the central plane is where you get the maximum stress, and you can cut through the central plane and do a 2D analysis, and you'll get accurate results. So here's the this is the mesh sequence. Here's what happened to the mesh size around here. There's a little mesh. If you call that H, local H, that's small, I know, but I'll make it bigger here. So the person doing this analysis started with a pretty good mesh around here. There's 16 elements there. And then they religiously halve that. And the number of elements, they have a different mesh out here. This is all very structured. It's a very nice mesh. And there's some sort of transition to bigger elements out here. But the number of elements goes up by about a factor of 4. Within 2%, within 1.3%, this quotient goes up by 4. The mesh in the critical region is perfectly structured, and the HM equals 2 upon HM minus 1 exactly. Okay. And elsewhere it does so, not quite so exactly, but pretty well. I would point out with these AQ elements, this final mesh 4 has about 500,000 degrees of freedom. What does that mean? Well, at every node you have 2 degrees of freedom, displacement in the X and Y direction. Altogether you have about 500,000, and you have to solve for those with finite elements. That's what you have to do. This tells you how much computation you've got. You can do several million. So this is not the limits of today's computers, but it's going to take a wee while. This is going to take a few minutes, and you're sitting at your desk. Here's the result. Sigma M here is sigma max at the fillet. Divided by the maximum bending stress in the smaller section. Okay, that's the biggest nominal stress you've got in this problem. That's from mesh M. The results. I should point out that you don't, when you're doing this here, you don't know exactly where this maximum stress is. You have to go find that. That's part of the analysis. And if you do a problem like this, once you find that location, then you use that same location. You find that location on your finest mesh. You use that same location for all your earlier meshes, even if the maximum stress occurs somewhere else. Just a small detail. And that single max that to put it takes a little bit more to determine. You don't quite know where its location is as well. But at the same point, when the angles converge, you get the following values, about 2.
Wait, so Dr. Sinclair,
Yes.
is sigma m always non-dimensionalized?
That's a good comment. No, sometimes in practice, people give it in stress values, KSI and PSI, okay? It doesn't have to be non-dimensionalized. Some people just report actual stress values with units, which is fine. So that's okay. In the same things hold. And if you report them in units, when you do your error estimate, you'll have a delta sigma m over a sigma m, so the units will cancel. And so it won't matter. Okay.
Okay, thank you.
So is sigma m here essentially a KT value? Since if you multiply it, essentially a KT value, a
Yes.
stress concentration value.
Yeah. So when you non-dimensionalize stresses like that, you could call this KT, and some people present this as KM. Okay. Okay. And that's quite legitimate. You can present it as a dimensionless stress or as a estimate of the stress concentration factor. Either way. Okay. But either that's quite acceptable. I think by and large, in communicating with engineers, they like to see stresses. Typically in my group, we've non-dimensionalized them and they're reasonably comfortable with that. There's probably a few out there in practice who'd rather see the units, to see the stresses. But at the end of the day, it's not going to make any difference. You're going to get the same result. If you've done a good FEA, you'll be able to tell them exactly what the maximum stress is. They'll tell you what their M is. Okay, that'll get you this, and you can go get the stress. There is a slight advantage to doing it this way. It says, once you do it this way, it's telling you, okay, you can have any moment you like in this problem, any M you like, and I can get you the maximum stress from this number. Whereas if you give me a specific moment and I give you actual units, then I've just solved the one problem for that particular moment. On the other hand, it's pretty easy to go back and non-dimensionalize it. So it's not a big deal. This is slightly to be preferred because it works for any M. Okay, you can just go get this, a simple hand calculation, and you can get it. But it wouldn't matter if they were just units. And as long as you knew what the M is, you know just to change it. It's just going to scale linearly with M. So it's not a big deal. Anything else? Okay, here are some results. Now again, at the most you really want 2 figures is not too bad in stress analysis, and 3 figures is all you really need. But we're going to keep giving these to 5 figures because when we take the differences, we're going to start to lose figures, and we'd like to have calculations done to about 3 figures. So we've got 4 decimal places or a total of 5 figures here. I hope that's readable. 3, 6, that's a 3. Well, if you take the differences here, this is about 360. With all the 367, I think. This is going down more rapidly. It's not a factor of 4. Quadratic convergence would be a factor of 4. Linear convergence is a factor of 2. Okay, and these are 8Q elements. So we expect to get faster convergence. That's what getting. Really, we might want to have another decimal place here to get this more accurately, but this will do for us. So 1 is satisfied. So we can estimate the error in epsilon 3. It's going to be this difference, delta. Divide by the value. Then the ratio of the two differences. And that gets 0.27%. And C3, read this over this, the log of that. And that turns out to be 1.6. Two comments here, and then we'll take a break. These are error estimates. It doesn't make much sense to give them to more than two figures. So if the error turns out to be 1.27, you just say 1.3. And once it starts getting less than 0.1%, you don't give extra decimal places. Just limit the number of decimal places to 2. These are estimates. This all seems a little inconsistent. We're giving these stresses to 4 decimal places, perhaps even 5 occasionally. That's because we're taking differences. But once we get this final error rate, we calculate it accurately, just give it to 2 figures. It is just an estimate. And this thing is just an estimate too. So 2 figures is about all you need here. Okay. All right, well, I'll come back and finish that in a little bit. It's about time to take a break. And I'll give you the results. Are there any questions on that so far? Okay. All right, let's take a 5-minute break.
Yeah, quick question.
Sure.
How are we going to apply this stuff to our course? Like, what information is beyond this class, and what information is being used in this class?
Okay. Well, if you look at problem set 3, I don't know if you've looked at it yet, you're given the stresses, and then you just check the convergence and guesstimate the errors, okay? And then you might have to classify them. So the classification is less than 5% is satisfactory, less than 1% good, less than 1/5% or 0.2% excellent. And so what you need, you won't have to develop any finite element analysis, okay? You'll be given values, and they'll be from a mesh sequence that's been properly refined. There'll actually be values. I won't make these up. These will be values that people have got, right? They've got them from problems. Some of these problems will be test problems, we'll know the answer, some of them won't. So you'll be given that, so you don't have to worry about that. At some point, you're going to want to learn how to use one of these codes, or it's very likely you want to learn, but that's not part of it. So what you need to be able to do is to decide whether they're converging. That's whether equation 1 holds. Way back when. These are your basic convergence requirements. Okay. Same sign and decreasing magnitude. If this doesn't hold, then you cannot do an error estimate. Not just you, but anybody can't unless you're doing this. Then you need to be able to apply this to get the error. You could conceivably be asked about the convergence rate. This is secondary. Okay. It's of some interest. And here it's 1.6, and we expect with these 8-node quads that it should be approaching 2. Well, 1.6 is a lot closer, well, not a lot closer, it is closer to 2 than it is to 1, which is what you'd expect with these elements. On the other hand, in very early meshes, sometimes you get a lower convergence rate than this. So, so that's what you're responsible for. But you're not responsible for doing any of this finite element analysis. You'll be given that stuff, okay? Did I answer your question?
Yes.
Okay.
I had 2 questions about the homework, but I'm happy to ask them now or at the end of class.
Maybe at the end of class.
Okay.
Okay. That'll be a little bit off what we're talking about right now, but I'll be happy to try and handle at the end of class. And anybody else can listen in then. Although I don't have problem set 3 with me, but perhaps I should have. Okay, let's take a break for a couple of minutes.
Hey, MD, just a heads up, you're unmuted.
Hello?
Just a heads up, you're unmuted and we could hear your keyboard typing in the background.
Okay. I'm in different room, so I'm going to the Dr. Sinclair room now.
Sorry? Okay, let me finish off this example. Here are the two error estimates. You can't have an error estimate for mesh 1. You don't know if it's converging. You can't have an error estimate for mesh 2. You have to have 3 meshes to decide things are converging. Then if they are decreasing, you can get an estimate for 3. You can't get an estimate for 2. Okay? And here you've got another 3 mesh sequence. You can get an estimate for 4. This first estimate is just what we had before. According to our classification, this is less than 1, so it's good. Okay. On the other hand, it goes down by close to a factor of 4, okay, because we've got these higher order elements. And so now it's less than 0.2%, so this is excellent. The convergence rate here, this is 1.6. Again, just 2 figures, and actually it's 1.8. So it's tending towards 2, which is what you'd expect with these elements in a smooth problem. So, so you would take KT as this dimensionless stress sigma 4, and so you'd say, and now you only went 3 figures, 2.09, and you say the error is plus or minus . We always say plus or minus, although you could say it's converging from below, and it's probably minus, but we never give a sign to the error. Okay. But there's been some reasons for that. Okay. But I can understand if you just said it was minus. Photoelasticity. Well, Wilson and White, sorry. And this is reported in Peterson, but you have to go get your paper, because what you get in Peterson is KT is 2.0, but you won't have the error. If you go get their paper, you'll find there's some scatter in the results. That's plus or minus 0.1. So that range is 2.1 to 1.9 and includes this value. So these two check. If you went and used your book, when I read that off, I got KT as 2.0, which is not surprising. They would have got it from Peterson. Okay. So this is a case where you've verified your finite element analysis, and then you've compared with somebody's experiments and they agreed. So this becomes a verified and validated result. And this is the result that's more accurate than this. This has got more scatter than this. Okay. 0.1 out of 2.0 is about 5%. Those are more accurate values. But the two agree. And that's typical. The scatter and photoelasticity often 10%, and that's what people that are good at doing it. And people who don't give you scatter usually have bigger errors than that. So 5% is good when photo existed. We could actually do another TTP for the shoulder and see how well these error estimates work. This TTP stands for Tune Test Problem, and you construct it. And we did this. So we have the same geometry and same message. And we got the following. I won't give you the detailed final element results. I'll just give you the end results. A table like this. 4 meshes. Similar sorts of errors. Convergence rate. Just so you see how it's varying, I'll give this the 3 figures. So it's tending towards 2. This had an exact answer. .4 exactly. We used to have about 2.1, so this is up by 15%, something like that. It's a little bit tougher problem. But now we know the true errors. We can take the value, I didn't give you the value, but we can take it and get the following. So the error estimates are working pretty well here. This is just bigger than 0.2%, so this is good. But so was the actual error, it was good. And these are both excellent. So what we're getting here consistently is these error estimates are a little bit bigger than the true error when we do test problems, and we know it. Sometimes we don't know what this is, but when we know that this is the case, but at the same level. Okay. And that's generally been found to be the case for the error estimates I'm giving you. They're conservative, okay? And we've done, I don't know, more than 50 test problems at this point, probably closer to 100. And we've consistently found that they're about 90% of the time at the same level. Sometimes they're not. Sometimes because they're conservative, they would say the true error is good, and this would be a bit bigger, and say it was just satisfactory, in which case you'd run an extra mesh to bring it down to good. So there's a little bit of extra effort involved. But let me do a different sort of concern here. Any questions on that? So this here validated this result, and this is the 2.1 is the right result for this thing, with 2.09. Okay, it's validated. And these error estimates here are very similar to here, and we had them confirmed here, so they're working pretty well. Let me do a problem that's symptomatic of something else. This is taken from this book. Let me give you the reference now. And this is a good book to learn how to operate answers. It's published in the latest, 4th edition, is published in 2015. I'll show you the problem from the book, and then I'll do a sketch of drawing of it. He's going to run you through the finite element analysis of this. This is a bicycle wrench. It has a pressure load in here. Okay? It's got a nut here, so it's fixed all the way around in this thing here. And the question he asked you is, find the thickness of this wrench so it could take a pressure of 88 newtons per centimeter, which is not a strictly correct SI unit, but what the heck. Okay. And so he gave you a pressure and said, okay, well, size the thickness of this wrench so it doesn't break. Okay. So let me redo his problem. So here it is. This is where the nut is. So this is held. This can't move, which is not a bad assumption for a nut. Then there's a slightly bigger in his figure, but I won't worry about that. Another empty bolt hole here, and another one over here. I'm just going with the pressure P. Okay. This is clamped. Reflect the nut. And I'm going to pick this point here. If you did this as a beam problem, you get rid of all the bolt holes, and you clamp it here, like a built-in end here, and you put this load on here. This part of the beam sticks out beyond the load. It has 0 nominal stress, so you can have low stresses. And what Movini asked you to do is find T, the thickness. So that the maximum stress was less than or equal to the yield strength. Well, here's what happens when you do a finite element analysis. I get the maximum stresses there. We'll divide them by P. Okay. We're going to do 4 cubed. And we'll halve element sizes, although this mesh will not be that structured. This is what we got. But as I said, this is lightly stressed here, so the first stress is about 5% of the pressure. As we refine the mesh, about 6%, but it's growing. It gets up to 11%. Okay. So if we get our delta sigma m, they're growing too. You don't pass the conversion requirements, so you can't report a stress here. So you have no error estimate. So we can't solve this problem. Well, the reason for that here's this piece of the wrench. We were looking at the stresses here. If you have a local radial coordinate r, then the stresses you can show this with asymptotics. So actually the problem posed in Moavini is impossible. It's impossible to run a finite element analysis and find a thickness because there's stress singularities. So stress singularities stop you doing anything useful here. What would you do in practice? Well, here's what you could do. If you had a problem like this, you could go get your cell phone and take a picture of this and then blow it up till you find out what the radius is in here. And then you could put a radius in and you could actually get it. Okay. You might find that the thickness started to be a lot bigger than what's done in practice. And that's because this local high stress would have a very small region. And so the yield strength would have gone up because like a small region. Okay. But that would be meaningful. Just doing a finite element analysis of the configuration given Moavini is meaningless. Something you want to avoid. But at least if you did this and did a conversion check, you at least know not to report a stress. There is no stress that you can report here that's worth anything. Now, I didn't do this to pick on Moavini. I think I mentioned that because I've taught finite element, I've got about 10 or so books. There's only one book that doesn't have some singular stress problem in it. That's that book Cook, which I think is the best book. Though Moavini is a better book in terms of linear answers. But there are about 50 problems in those other 9 or 10 books that are singular with no mention of being singular. This is a common failing and it happens in practice. Are there any questions on that? In fact, in this problem here, there are a lot more singularities. There are something like, let's see, at every one of these corners is singularity, 3, 6 or 18. Another 8, there are 26 stress singularities in this problem. Okay? Every time you have a discontinuity like this, it may look innocent, you've got a singular stress. If you really want to know what's going there, you need to go find out what the radius is. Typically, you probably don't. The way you would design something like this, you'd look, these things have been built, you'd go test it and see does it work. Okay. So, well, I wanted to show you something from industry to show you that this is still a concern. And so I'm just going to present this to you. There's no need for you to take any notes on this. I guess if you want to see it, you can get when Mohammed posts these lectures, you'll be able to see these slides. But let me show you. This is an example from industry. Okay. I've got a couple of slides here that will show you. I think I have. Here we go. Yep. when you have a gas turbine, the blade that goes up here, that's spinning about 30,000 RPM. This is the segment of the disc it's in, okay? These lines, it's not drawn to scale. These lines are sloped too much. There'd only be about a dozen blades if the slope was right. The slope is more gentle. There's about 60 of these blades. And what happens is that cracks initiate here, or here for that matter, and eventually the crack grows and the blade leaves, okay? Alternatively, sometimes the disc itself, there's another blade over here, this starts to grow, and this chunk of the disc comes off, okay, and then two blades leave. This has been a problem for some time. I got involved with this in 1996. The Navy was not happy, or wanted some improvement on the final element analysis being done at GE, and somebody suggested that my group might be able to do that, and so we got involved on a consulting basis, trying to analyze this and understand these stresses better so we could alleviate the situation. GE came up with its own way and doing this stress analysis is not trivial, but we did all the conversion checks and everything else, and you have to have a thing called sub-modeling to get these stresses, where you have a mesh for the whole area, then you have a little local mesh and you pick up boundary conditions around there. And other people have done sub-modeling other than just our group, but we had some ways of checking the errors and making sure it's okay. But GE themselves, actually GE were not that thrilled to have me hired as a consultant because they lost some money, but eventually we got a research grant from the Navy. The other thing that interested me was these are airplanes and engines. Why is the Navy involved? Well, it turns out Navy has Navy officers fly their planes for aircraft carriers. And when I first went there, I had a beer with the leading officer afterwards, and to try and try and make me very interested in solving the problem, he said that for about the last 10 years, he'd been losing two or three planes a year to this. He didn't go into specifics. I'm not sure he was supposed to tell me that, but he wanted me to take it seriously. He's a decent guy. And I imagine what happens is that these are high-speed planes. They don't glide that well. They have very skilled pilots. But if you've got a high C, you're not going to be able to land this thing, I don't think. So you're going to get out. The pilots are live, but the planes are. But he didn't discuss it that much. But anyway, it's a serious problem. And so GE came up with a way of alleviating this. And it's similar to what I showed you in the beginning of class. So it has, this is the underlying idea. And they had, when I was brought on board in 96, they already had this pattern and they were starting to test things. And the idea is if you have a crack and you put a hole at the end of the crack, it's like the first two specimens I pulled. This has less of a stress concentration, and so the cracks tend to stop growth. And this is used in the oil and gas industry too. Well, you can't start drilling holes if you've got liquids inside, but there are certain situations where you can slow down. So their idea was, well, we're going to remove this highly stressed area. And the highly stressed area up here at C, this is the highly stressed. So we're going to remove this material, okay, and lower the stresses. I've never seen their finite element analysis, but they said in their patent that the stresses went down. And I know some people at GE, and so I got some informal estimates. There's a dimensionless stress, and what their finite element they found was with an undercut, the maximum stress was 2.9, or about 3 times. Without the undercut, it was 6 times. And if you can start dropping the stresses by a factor of 2, you're going to get much better fatigue life. So that's what they said. On the other hand, they didn't do any convergence check. Okay. Well, because I've been told this number, we refined our mesh. We actually had several meshes before this. Okay. Our job was to do this thing without the undercut. That's what we were hired for. But later on, out of interest, I did this thing with the undercut. And we had to have a couple of meshes to get to here. Okay. This was a pretty fine mesh. And to keep on going, we had to use a sub-modeling technique. But when we kept on going, the stresses increased. Okay. Now it's actually bigger. Oh, we did this analysis and we got about 6.1, a fully converged result without the undercut. Well, now we're up to what is the undercut. Now we're ahead of it. And the reason for this is these stresses are diverging, so there's no estimate. And you can do asymptotic analysis and show that it depends on the coefficient of friction. This is a singular stress. So does this sort of stuff happen in practice? Yes, you need to avoid it. You need to check your convergence. If it's not converging, you don't say anything about the stress. Now, this is a complicated situation. Some other things may be happening here. It's a fatigue situation. It might have worked, but it wasn't going to work for the reason they said. Okay. They've spent between $5 and $10 million a year testing this for 20 some odd years. It's not solving the situation. In Hara Airport, about four or 5 years ago, something like that, most of these blade attachments come off in military planes. Military planes are designed to the limit, okay, to get the power to weight up. But these engines are detuned for commercial. And to the best of my knowledge, these blade attachments hadn't come off in commercial planes, but there's been 2 in the last 5 years. So this is still a problem for GE. And the one in Hara Airport, the blade went about a quarter mile and went through the side of a building and started burning the floor. Another one, the second one that happened after that, it went through the side of the airplane and a woman got sucked out of the gap and she died. And so this problem has not been solved. And to base an approach on faulty finite element is not good engineering. You need to always do these convergence checks. Okay. Now, I have an approach now which may alleviate this thing, and we'll probably go and talk to GE maybe next semester, but it doesn't involve any undercutting. So when you get out and practice, don't start giving stresses from one mesh and basing engineering decisions on it. Do your convergence checks. You'll get things wrong otherwise. Now, I wanted to say,
due to this, I was in the military, I was in the Air Force, and due to what you're talking about now, we had to do special inlets and exhaust inspections after every flight before the planes could fly again. And
yeah,
we continually drop the engines and rebuild them.
yes. Well, what happens here? What happens here when you get these cracks in this thing here is it doesn't come off immediately. And so if you inspect, and I don't know what today's inspections level are in the military, but probably any crack that's more than a 64th of an inch, you can see it. And then because it's in a dangerous situation, you pull it, okay? And that's expensive, okay? Doing that's expensive. If you know what's going on better, you can even leave engines up there with a few cracks in them. It's good retirement for cores. And then you don't have to replace them anywhere near as often. But these blade attachments are a problem, okay? But here's the lesson for you. I mean, these were a couple of experiences. They went up into management, okay, these guys. And one of them is quite an inventive guy, but they didn't check it out carefully. And GE spent a lot of money testing this. And I'm not privy to the results, but informally I've been told that it's a mixed bag, that they're not getting good results. And the fact that they've got 2 GE engines in commercial planes that have lost blades, that means they haven't solved the problem yet. So there's something needs to be done. But the key point for anybody is, when you get a finite element stress, make sure you've done a convergence check. So you're not telling somebody this is a really good stress. In this case, that was wrong. The reasons for doing this were absolutely wrong. Okay. It's a complicated enough problem. It's not quite as simple as all this. And there may have been some alleviating aspects of this, but not from what they did. Okay. All right, now what I want to talk to you about the test. So I got an email from a student a bit concerned about the material we're covering for the test, and I thought it was better just to do what I did today and redo the convergence checks and stuff like that, and not introduce contact problems. Just do contact problems after the test. Number 7 on problem set 3, don't bother doing that. Okay, if you've done it, looked at somebody's answers for contact problems, okay, it won't have hurt you, but it's not going to be on the test. Okay? And you don't need to hand it in on Wednesday. Okay. What did we get? All the examples I've done in class are representative of sort of things that you could be asked on the test, okay? Except number 4. Number 4 was a derivation of a 2D stress analysis, just to show you where that stuff came from. You haven't had enough 2D stress analysis to be reasonable to have a question on that. So, but anything that's been in these examples or in these problem sets otherwise, other than these 2 exceptions, are fine. Okay? There are some sample problems in the beam, in the book, but there's only a couple. SP is sample problem 4.1 for straight beam. There's some curved beam there. Curved beam theory is quite useful. Okay. We started a bit late, and I thought it's more important to do the FEA than curved beam theory. But the book doesn't do a bad job of curved beam theory. If you start encountering curved beams when you get out, you could go look at the book and figure out how to do it. But it's not in this test, not in the course. Mohammed did a very brief treatment of it, but that stuff's not examinable. Okay. There's also a sample problem 4.3. I've forgotten what 4.2 is, but I don't think it's appropriate. And 4.3, but the book likes you to draw more circles. I'm not going to ask you to draw more circles. Okay. If it helps you solve problems, okay, but it's not going to be on the exam. I posted this. It had the first part of this is references. The second part is a practice test. The practice test is largely test 1 from 2018, the last time I taught this course. But they did some curved beams, and so that's been taken out. They also did some torsion of non-circular sections, which is in the book, and that's been taken out. And so that's explained in the front of this practice test. On the other hand, they didn't do convergence checks for finite elements. There's some problems like that in problem set 3, and so that's fair game for you. So they covered slightly different material, and so it consists of 10 short answer questions and 2 other questions, 3 questions in all, each worth 10 points. And so I think the last question, 2B, 2B was about a curved beam, or 2C, I think. A and B is okay, and 3 is okay. And then one of the short answer questions was missing, something like that. Or might have been a couple, I put another couple in. So you can see that. I will post solutions for this. The solution to problem set 3. And I'll go through them in class on Wednesday. Okay. And I'll post solutions to the practice test on Thursday. I don't post them right away because in my experience, that has not helped students. Students look at it and they look at the solution and say, this is easy, okay? And then when they get in there, they discover the same level of test questions is not so easy when they're doing it themselves. So it's much better for you to do it yourself. But I will have office hours on Tuesday and Thursday. And I'll be at home. So if you've got a question about these solutions, I'll post them earlier in the day on Thursday. If you've got a question, you can send me an email or you can call me, okay? And yes, I'll answer your question in a minute. Yeah, and you can call me, or I'll call you if you send me an email, okay? But include your phone. So the format for this test will be exactly the same, okay? So it'll be 3 questions. They'll each be 10 points each. Question 1 has 10 parts. Occasionally it'll have a double part, occasionally it'll be part A, part B, and then part C and D will be about the same problem or something like that. But they'll have 10, they're going to be 1 point each. Okay.
Do you give partial credit?
Sorry?
Do you give partial credit or no?
Yes, yes. But on these short answer questions, the way the partial credit goes, if you get the right answer, obviously you get 1. If you get the right answer with the wrong units, you're going to lose 1/4 point. Okay, so get your units right. Okay. If you get the wrong answer, but you've written down or you submitted the right formula, you just haven't implemented it correctly, you get 1/2 point. Okay, so you need to pick off from your sheet the right formula to solve the problem. Occasionally, it might be two formulas needed, in which case you'd have to have them both, get your 1/2 point. Okay, but then you have to implement that formula correctly to get the whole point. When on these other questions here, if you have an error in your units, it'd be 1/2 point off. And we'll look and give you some partial credit here, but you want to check your work. Okay, engineers get credit for getting right answers, not for sort of knowing what they're doing and getting right answers. So check your stuff. Over the years, I've given exams like this for over half a century, and there's been 3 students who scored 100%. Okay, they never left early. Okay, I don't know why you'd leave early, why you'd give in to the exam if you haven't got 100%. But people don't usually get 100%. But you want to check your answers. So you'd like to finish these. These are be half an hour each. Okay, you'd like to finish them in 20-25 minutes. So you've got 5 minutes to check. Okay, otherwise you're going to lose points for careless errors. The biggest mistake people make on one of these tests is they start doing these short answer ones and they spend too much time on a single part of those. Okay, there's going to be 10 of them. You've got 30 minutes. That's 3 minutes a question. They're worth 1 point. Don't start spending 5 and 10 minutes on one of these. That'll kill you. Okay, so the way I would favor doing this, if I were you, is I'd start on the first question and pick the short answer ones that you think are straightforward and leave the other ones alone, and then go do the long questions, okay, and make sure you've got them done, and then come back and finish the short answers. But don't, the easiest way to screw yourself in terms of time on this test is to start spending 5 or 10 minutes. We're still on one of these 1 point questions. That's not cost effective. Okay. Now, I'm somewhat sympathetic. I mean, part of being a good problem solver has been determined to solve problems, but you've got to channel this determination if you want to be successful in these tests. The solutions to this test, they'll all fit on 1 page for each question. So it's not long. Okay? It's not long if you know what you're doing. On the other hand, if you don't know what you're doing, you can easily spend longer time than that. But basically, you'll see the work solutions later on, and it's not long if you know what you're doing. So the key is to know how to do these problems, okay, and make sure you know that, and then prepare yourself a good formula sheet that says, okay, for these problems, what formulas do I need? What formulas do I remember? What formulas don't I need? What formulas from math do I need that I'm a bit rusty on or don't quite remember? And make sure you've got yourself that right formula sheet. Any questions?
There's a bunch of questions in the chat.
Sorry?
There's a bunch of questions in the chat.
They ask, will the exam be 1 or 2 hours?
1.5
can we-
hours.
1.5 hours. And
Sorry,
can we
I should have said that, 1.5 hours.
and can we take the test on a tablet?
I don't know what?
On a tablet. So in other words, download the exam and then write on our computer.
Okay, I'll let you know this is the first time I've used Zoom to give lectures or give an exam. So I'm going to find out just what the rules are going to be for this test, and I'll let you know Wednesday.
Okay.
Okay.
In terms of the interaction, but I've never done this, so I'm not quite sure. But I think one of the things we want you to do is to set your cell phone up so it gives a photo of your workspace, so we can see where you're working. Okay, but these are half-hour each questions. I should have said that.
Are you still offering in-person optional?
No, I didn't get enough students who wanted that, and it takes quite a bit of manpower to watch this number of students doing it on Zoom. Okay? And disability services will be doing people who get extra time. But I'll go check with them and figure out how that works too. For these
Okay.
exams. So no, we don't. If there'd been like 50 of you wanted to take it in person, then I could have supervised that and had other people supervise the Zoom thing, but I didn't get that sort of response. So no, we're not going to be able to do that. Any other questions? Okie doke. Well, we'll see you. Oh. Yeah, this test one is on Friday. By 30 to 10.
And questions 2 and 3 are just going to be like longer questions.
Right, more like homework.
Okay.
Okay. They could have parts, okay, but you can look at the practice test and you'll see the sort of questions. Oh, I should point out one of the questions on the exam for 2018 was a problem I did in class this year. Well, they had not had this problem in class, let me tell you. Okay. It was taken from the book, okay, but they had not had it on a homework set, nor was it done in class. Okay. So when I say understand how to do this, you will not get exactly the same problems, okay? And you might look at that practice test and say, oh, look at this. That was done in class. I forget which example it was. Okay. Well, that didn't happen for those students. I did a different problem on some sprockets on a shaft, I think, in class for that one. And they didn't have it in the homework. So, but it is something you do. Any other questions?
You said you were going over the answers to the homework. You said you were going over the answers to problem set 3 on Wednesday.
That's right.
Okay, then I'm sure you'll answer my questions on it then.
Yeah. So, well, you go ahead and give it your best shot now, okay? And you might start trying to do the practice test so that you start getting prepared. You know, in an exam like this, it's how well you think, and you don't want to be working late on Thursday night. I imagine you already discovered that, but you know, working late and not getting much sleep is not a good way to prepare. You're better to work in the day on Thursday or Wednesday, getting ready. I would do this practice test if I were you before Thursday, and then if you've got some, then you get the solutions and you can go look at them. And if you have some questions, let me know. If any of you, well, this is true of the notes I'm giving you, or of any of the solutions, if you think that there's an error there, let me know. Typically, what's happened is rather than be an error there, a student who's raising the question didn't quite understand something, in which case it's really important to raise what you think is an error. I'm not saying the solutions are completely free of errors, but it's really usual for my solution to be pretty much that way. But and the same thing, I'll check the notes I've given you today, and if there's any errors, in what I've given you, I'll let you know Wednesday. But if you think there's an error, that means I haven't explained something as well as it could be, and your understanding is incomplete. So by all means, and you may have found an error. By all means, let me know. And if there is an error there, I would like to share it with everybody in the class.
So I did have a question about unit conversions.
Okay, which one?
I see on the practice test, there's the question about, you know, an engine delivers so many horsepower. Would we be able, would we be given the conversion factor for horsepower? Or just...
No. I mean, if you look at your homework problem, okay, I did give you the conversion factor that time there. That's the first time up, okay? It wasn't done in class, but after that, you need to know, okay?
Okay, would that be things that we'd be allowed to have on our formula sheet?
Oh yeah, sure.
Okay.
Sure. So that problem is, they would have been told in class that 550 foot-pounds per second is 1 horsepower, and they would have to know that, okay?
Okay, perfect, thank
you.
You said, what time did you say your office hours were tomorrow?
From 3:30 to 5:30.
Okay, and then just email you, and you said you might call us or something?
Yeah, well, I'll look at your email if I can answer it.
Okay.
You've got to bear in mind that my typing speed is about 1 letter per 10 minutes or something like that. I have to find the darn letter on the keyboard and all this stuff. So if the answer to your question is going to be a lengthy email, then I'm going to call you, okay? That'll go much faster. If I can give you a short answer, okay, like 2 words or something, then that's fine. But I'll respond right. But I'll start responding from 3:30 to 5:30 tomorrow. Okay. Don't expect responses before that, but that's when I'll be responding. And you can send emails to me, I guess, anytime. I tend to be one of these people that only looks at emails, you know, once or twice a day. So I don't sit there and immediately respond to emails when you get it. But I try to respond on about a daily basis. But for questions about problem set 3, in particular, 3:30 to 5:30 tomorrow, and then questions about the practice test, 3:30 to 5:30 on Thursday.
Okay, thank you.
Okay. Anything else? Okie doke. See you Wednesday. Well, in effect. Cheers.